All right, so I'm going to go over the problem number 3, or the supplemental problem on our simple harmonic motion assignment. And so let me screen share here again. And so the last two we did were pendulum problems. This one is a mass on a spring. And so what we have is we have a mass that's stretched and mass attached to a spring that's then stretched. And then you attach that mass to a cord, a taut cord, so it holds it there in place. So right now, this diagram you're seeing is a stretched spring, and it's staying in its equilibrium position because it's attached to this cord here. And it essentially doesn't give us any numbers, but it wants us to solve some of these problems in terms of mass, spring constant K, and force of tension. And then fundamental constants. And so the first time I did this, I didn't put it in terms of those. And so just be careful when you're solving these. You might get an answer that's algebraically correct, but it's not what they're looking for because they're specific about what they want the final answer in terms of. And so let me stop screen share here. All right, so that's the setup. And the first part of the problem wants us to draw a force diagram. And so I'll draw a dot again to represent that mass. Well, that mass is on some horizontal surface, so we have a normal force, keeping it from falling through the floor. We have a weight force going down. And then we also have these two forces that are balanced here. We have the force of tension, Ft, and then we also have that spring force, Fs, going this way. And these are all balanced. And so what I want to do now for part B is to solve for, let me make sure I read this correctly, because now that I have my force diagram right here, I think the rest of the problem should kind of fall from that. But what it wants us to solve for is the distance that the spring has been stretched from its equilibrium position. So based on this diagram right here, the spring has already stretched some amount, and it's staying that way because of that cord that's holding it there. But it wants to know how far it's been stretched. And then it says for parts C, D, and E, it says the cord suddenly breaks, and so it moves to the left. Calculate the speed of the block when it has moved half the distance. So actually, let me just go back to my, let me just solve for B, and then we'll come back to C. And so for B, it wants to calculate how far that spring has been stretched. And so I'm just going to write my equations for my forces and then see if I can come up with some way to solve for that. So I know that my force of the spring is equal to the force of tension. This would be like my x direction. And in my y direction, I know that my normal force is equal to my weight. And so I say, okay, that's all I have to work with. What can I do? Well, my force of the spring is also called Hooke's law. And I know that I can write that. So I'm going to look at just this x value. I know I can write that as K times x, where K is the spring constant, x is the displacement, is equal to the force of tension. Okay, and I say, okay, well, great. I don't need to even worry about the y equation because I can write this, the distance that it's stretched, in terms of my fundamental constants, or the algebraic variables that they give us. And so I can say that x then is just equal to the force of tension divided by K. So our answer then would just be Ft divided by K. All right, so the next part of the problem says, now we cut that string. So the mass is now free to oscillate back and forth, and it wants us to calculate the velocity when it has moved half of the distance to the equilibrium position. So keep in mind, if you have a mass on a spring like this, and this is equilibrium position, x is equal to 0, and it was being held by this string that's attached to the wall. It was being held at a distance x, like that. And so as it's cut, it oscillates back and forth like this. It wants to know the velocity halfway between that point where it was cut and that equilibrium position. So it wants it to know, essentially wants to know what is the velocity at that halfway mark, halfway between equilibrium and halfway between the point where it was cut. And so again, when I think about velocity, I always think, can can I use something involving energy? That's usually the easiest way to go about solving for velocity. And so I say, okay, well, initially, before the string is cut, we're dealing with all potential energy of the spring, right? It's not moving, so there's no kinetic energy, but it has some energy associated with it. We know it does because as soon as you cut it, it moves back and forth. And so therefore, your spring energy is going to be your total energy. And then halfway between oscillations, it's going to be moving, but it's also going to have some energy still left over in the spring, right? If it's at its equilibrium position, then all the energy is in the form of moving energy and kinetic energy. But in between that equilibrium position and in between that, that farthest distance where it momentarily stops, that has both kinetic and potential energy. And so therefore, this is going to be equal to some potential energy of the spring plus some kinetic energy. Well, I know the potential energy of the spring initially is just 1/2 kx squared. And I know if it's halfway, after it's cut, our final energy is going to be the energy of the spring when it's halfway between that, the equilibrium in that place where it was cut. So I know this is going to be 1/2 k times x divided by 2 squared. And then I know my kinetic energy, of course, is always just 1/2 mass times velocity squared. And so this is plus 1/2 mass velocity squared. Except for, and I say, okay, I could solve for it. And this is where I bring up in the beginning of the video, I said I wasn't careful about this, but I could solve this equation pretty easily for velocity in terms of this x. But they don't want you to solve it in terms of x. They want you to solve it in terms of the tension, the mass, the spring constant, and any fundamental constants, but they don't want it in terms of x. And so therefore, from our last part of our problem, we say that x is equal to F sub t divided by the mass m. And so therefore, or sorry, not divided by mass m, divided by k. And so therefore, I need to plug in this value into here and then simplify. And so I'll just do that then. So it's 1/2 k times x squared. So that's F sub t divided by k squared is equal to 1/2 times k times x, which is F sub t over k divided by 2 squared plus 1/2 mass velocity squared. Okay, that's kind of a messy equation. But you can see that you can simplify it quite a bit. And so I'll leave the algebra up to you. But you know, right away I can see that one of these k's is going to cancel here. So I'll simplify it just a little bit. So I'll say that it's 1/2 times F sub t divided by k. Because one of the k, if you're squaring this, oh, there's a square there. If you're squaring this, we have a squared k down here, and that will cancel out there, is equal to 1/2 times k. And actually, I'll erase this k because that's going to cancel. And so again, you're left with F sub t squared over 4 times k, like that, plus 1/2 mass velocity squared. Okay, from here, we can simplify everything down by a bit. So what I would do, I'll write the final answer, but I'll just tell you what I would do. I would, well, the halves cancel because they're in every part of this equation, or every variable, every term in this equation. So the halves cancel like that. And so I would then bring this over to the other side and then just solve for the velocity. And so when you do that, you should get a velocity equal to F sub t divided by 2 times the square root of 3 divided by k m. And so this would be your final velocity there. All right, there's a lot of algebra there, but hopefully it's the hard part is the algebra, not necessarily the physics. And so this is your final answer here. The last part of the problem, the last part says, oh, there's 2 more parts. It says to reach the equilibrium position. Oops, sorry, I'm reading the wrong thing. Okay, so part D says calculate the time after the cord breaks until the block first reaches its position furthest to the left. And then part E says suppose instead that the friction is not negligible. It wants you to calculate the acceleration of the block just after the cord breaks. All right, so the first thing is how long does it take to reach the farthest position to the left? And so remember our period, that's what we're gonna make use of. Our period is one complete oscillation. So our period would correspond to going all the way to the left and then all the way back. But we're only looking for the amount of time it takes to go all the way to the left. And so that's going to be half of the normal period. And the period is given by, when you have a mass on a spring, it's given by 2 pi times the square root of mass divided by k. But we're looking for half of this, and so it's just equal to pi times the square root of mass over k. So that's our period. And then the last part says, okay, now assume that there is friction. What is its acceleration? Well, if that's the case then, going back to my force diagram, I would say that friction is going to oppose the motion. And so therefore, we're only dealing with one extra force. And so we have F sub T to represent the tension. That's what's going to pull it in one direction. And friction is going to oppose that direction. So it's going to be in the opposite direction. And so that's going to be minus F sub F for the force of friction. And it's going to accelerate, so we're going to set it equal to mass times acceleration. F sub T, I'll leave there, but we know that the force of friction, so I'll write F sub T, but we know that the force of friction is mu K, the coefficient of kinetic friction, times mass times gravity is equal to mass times acceleration. I want to solve for acceleration, so I'll just divide everything through by mass. And so I'm left with F sub T divided by M minus mu K times G is equal to the acceleration A. So your final answer would be this right here. All right, so that's all of the problems from our simple harmonic worksheet. Let me know if you have any questions.